Welcome to this pre-recorded talk titled Secure Evaluation of Quantized Neural Networks, which is a joint work between me, another student from Aarhus University, and Marcel Keller of Data61. So we consider the following setting. So we have a client with an image, the small dog here, and a model owner with a neural network model M. And the client wants to know what's on their image, basically. So this, of course, is fairly easy if we don't care about privacy. The client just sends his dog picture to the model owner, who evaluates his network on it and then sends back the label. So this is all well and good, but clearly this doesn't work if we care about privacy. This provides no privacy for the client. And if we instead send the network to the client and then he can do the inference locally, that doesn't work either, right? Because now there's no privacy for the model owner. So, but we can fix this, at least theoretically, by just throwing MPC at it. So we consider this outsourced setting where still with the client and the model owner, but now instead of doing the computation between each other, they outsource their computation to a set of servers. And the way they outsource this is that they secret share their data to each of the servers. The servers run a secure computation, and then the result is given back to the client in this case. And the guarantees is that in this case, say none of the servers collude, then the privacy is preserved of the inputs, so of the picture and the model. The nice thing about this outsourced model is that ideally, at least, we could imagine that the model owner and the client do not need to know what goes on under the hood, so to speak. They don't need to know the particularities of how these servers are actually running the secure computation. Unfortunately, in practice, this is not really the case. The model owner especially needs to be very much aware of what happens in the secure computation, because it provides, or it enforces a lot of limitations on what kind of model he can actually use. So I'll go over these issues now, because they're quite important. So first of all, of course, is that floating point numbers are not very easy to work with in MPC. In fact, they're quite hard. And the way that this is typically solved in prior works is that they discretize the model in some way. And there is, I want to highlight like two different ways of discretization here. So one is bits, where instead of actually having full like 32-bit floating point numbers as your weight, you actually just have a single bit. This is what happens in this XONN paper from Usenix last year, or from this paper by Bors et al. From 2018 from Crypto that year. Of course, produces smaller models, but it's also quite difficult to deal with. Another approach is, of course, to just use fixed point instead. So just instead of floating point numbers, we use fixed point numbers. And these are a lot easier to work with in MPC. Not for free, of course, but at least they're more efficient. But the question for both of these is, of course, when should this discretization happen? Should it happen during training? Should it happen before? Well, when I say before here, I mean during training, or should it happen after training? So for fixed point, we can probably get away with doing this after the training has concluded, right? We take our floating point model and then we just treat all the floating point values as a fixed point, or we do a fixed point approximation. And this probably works. So that's well and nice. But if we want to use a more aggressive form of discretization, these binarized networks where weights are bits, then for sure this has to happen during training. So if our servers use this like these binarized protocol, or the protocols that work with binarized networks, then the model owner needs to be aware of this, of course, because he cannot input a floating point model and expect it to work on these servers, because they can't do any training. They don't know the training data that the model owner used. Another question here is, of course, what happens to the accuracy? It might be the case that if we choose some bad fixed point parameters, for example, then we're going to lose a lot of accuracy in our model. So the model owner, again, he needs to be aware of what would be acceptable parameters, fixed point parameters here. Another issue is that nonlinear functions are expensive. So a neural network is essentially a linear operation, then a nonlinear one, then a linear operation, then a nonlinear one, and so on and so forth. So there's a lot of these in a neural network, and if these are expensive, of course, it's going to be expensive to do the secure prediction. One way to solve this is that we could just use gobble circuits. So this is what happens in Gazelle, which is this paper from 2018, or Delphi, which is a paper from this year. Both are from Usenix. But the issue is that this is, of course, expensive, and now we need to be able to switch between it. Now we need to have an MPC scheme that allows you to go from like MPC in an arithmetic world to MPC over gobbled circuits. And these are often quite expensive, or they require very specialized protocols where they work well. Another approach is we could use MPC-friendly activation functions. So this is what happens in the CryptoNet paper from 2016, or the SecureML paper. The issue is, of course, now, can we actually still train the model if we require to use some strange polynomial as all our activation functions? Then is training still possible? And of course, what is the effect on accuracy? Because now we're using different activation functions, and it's not exactly clear if these actually work as well as the original ones, so to speak. So these issues motivate the questions that we examine. So first of all, can we use existing ML frameworks to train MPC-friendly models? So this means that the model owner does not need to dig into the nitty-gritty details of the MPC. He can just use tooling that already exists, even if this tooling is not designed for MPC. Second question is generic MPC frameworks capable of performing secure inference? And why is this nice? This is interesting because then this cluster of servers that we outsource our computation to, they're no longer forced to behave in a specific way. They're no longer forced to run a particular protocol. In fact, they can use a protocol that is for which an implementation has been tested more, or there is more reference material in order to implement it, for example, and so on and so forth. So both of these questions are sort of like complementary to each other. And of course, for the second one, when we talk about performing secure inference, we of course talk about it in the context of the first question. If we can train these models, can we then use generic MPC frameworks to evaluate them? Okay, we have a number of contributions. So first of all, we observe that this idea of quantization that already exists in, say, TensorFlow or PyTorch actually does produce these MPC-friendly models, or produce models that are that can be evaluated efficiently in MPC. And this is interesting because it somehow shows that some of the issues that we face when we want to do secure inference are also faced in a different context. In this case, efficient inference on, say, a mobile phone, which is what quantization is actually designed for. Second, we show how to evaluate these models then in a black box kind of way. And the nice thing about doing it this way is that then we can take any instantiation of this black box and then we get the secure inference protocol. For certain kinds of instantiations, we provide optimized variants of certain subprotocols. So we have this like black box approach to the inference, and then for some of the settings, in particular the settings that are like the most efficient, we show how to like further increase the efficiency of these. And finally, we conduct a lot of experiments essentially to examine the trade-offs between the different MPC instantiations and efficiency for these quantized networks. And finally, also in context of this experimentation, we also benchmark these optimizations that we have against what's it called, CryptFlow from SMP this year, which is another three-party secure inference protocol framework. Okay, so this quantization. So I'll go over like why it works or why it's so nice for MPC. So we consider some values, these alpha i's, beta i's, gamma i's, which are real values or floating point numbers. And the way we approximate them is as follows. So we get some integers. In practice, these would be 8 bits, as well as some floating point numbers, these mi's. And then what we do is that we take this integer and then we shift it and then we scale it in order to approximate the original value. What we need to take into, or what we need to notice here is that these C's and these M's are fixed for many A's. So in particular, they will be fixed for say, for example, the entire filter of a particular convolution. And that makes it very nice, as we'll see in a minute. So let's say the gamma is the inner product of the alpha and betas. So this is essentially what we want to approximate or compute in a more efficient way. By using the fact that we now approximate our alphas and betas like this, we can rewrite this inner product like this, or moving stuff around, we get this formula. So this is essentially the one we will be using, or be computing securely. And this is very nice because this is a inner product over integers only. So these A's and C's are integers. Then it's a scaling with some value here, and then it's some integer stuff again. It's worth noting, of course, that since we approximate some values here, we need to ensure that these values, like that any error that is in this approximation does not grow out of control, basically. So there has to be a clamping operation surrounding this entire thing. And the clamping is just ensuring that the value is in a particular interval. So the question remains how to handle this M, because I just said that floating point operations are hard, and now we still left with at least one floating point operation per layer, basically, or per entry in the output, or per output. But we do as TensorFlow does, because then we evaluate the models exactly as TensorFlow does it, which is what we want to do. And what TensorFlow does is that it treats it as a fixed point number. And this is great because, as I mentioned before, fixed point values or fixed point encodings are a lot more efficient to work with in MPC. And this essentially just means that we can compute this multiplication by this real value M by a multiplication plus some shifting, bit shifting back and forth. And finally, activations, we get them essentially for free. So by picking these C's, C3 as 0, the M3 as this particular value, 6 over 255, then when we dequantize the output, the Y up here, we see that it ends up in this range, like guaranteed. It's quite easy, just input the values and see for yourself, I guess. And why is this nice? Well, it's nice because this corresponds exactly to applying a ReLU 6 activation. And this is essentially the idea of these quantized networks, so that by using this particular activation function, this particular encoding, then you get a model where everything is just bitwise operations or operations on integers, and yeah, you get like a very efficient inference for that, at least on embedded devices, and as we shall see also in MPC. So we want to compute this securely. So I replaced the M here by this M prime and 2 to the minus n, which is the fixed point encoding of this value. And now we put like brackets around everything, just to show that a value in a bracket is supposed to be kept hidden. Okay, so the first part of this equation that we want to compute is, of course, this inner product. And that's quite easy because it's in just a bunch of multiplications and additions. Interestingly, in honest majority protocols, this is actually particularly cheap because in those cases, the length or the number of terms in this sum has no effect on the communication cost. This one is a bit more tricky, so we can of course multiply by this integer m prime, but this corresponds to a left shift by a value that we do not know, and that's quite hard to do. So what we do instead is the following. So we pick a capital N here, which is an upper bound on the small n, and this will just be picked like independent of the model, so it leaks nothing, so we can have that public. And then we multiply by this value, and notice that this 2 to the capital N minus small n, that's going to be a positive power of 2, so we can treat that as a regular multiplication. And this value can of course be input by the model owner himself. So it does need to be computed securely, although that's also possible. What we do then is that we then truncate by n, and that's quite nice. So it's essentially we shift first to the left, and then we shift to the right. And this trick turns our right shift by a secret value into a left shift by a secret value plus a right shift by a public value. So that's quite nice. The downside is that this requires a bit of extra space because we need that this initial multiplication by 2 to the capital N minus small n, that doesn't overflow. We have this addition, that's for free, and then we have the clamping, which is just two comparisons, which is a well-known, well-studied, implemented all over the place primitive in MPC. And we need these comparisons to compute this clamping, of course, because we can express clamping a value to an interval as the small equation here. All right, so the kind of experiments we perform are as follows. So we download 16 pre-trained models from the TensorFlow repository. All these models have 28 layers and between 500,000 to a bit above 4 million parameters. These are these are called mobile nets, and they're designed they're called mobile because I guess they're designed for mobile phones. All of these are ImageNet networks, so they are networks which takes inputs that are like a couple of hundred bits per in each direction, and then they output, or then they classify this image into one of 1,000 categories. So they're quite large and they're used in practice, these models. And I want to stress that we take these pre-trained models and we don't do anything with them. Like these are just downloaded straight from the TensorFlow repository. We evaluate these models across all the different interesting thresholds, settings, corruption settings, and algebraic structures we can think of for MPC. So in particular, making use of the fact that we actually have this black box description of how you do secure inference. So more precisely, this means that we test this with 3 parties and 1 corruption, 2 parties, 1 corruption, semi-honest and malicious security, and secure computation modulo prime, and secure computation modulo power of 2. I will go over some of the results for these things, and in the paper we also have like a bit extra. I will focus mostly on like running times for this inference. In the paper we also have like communication, so you can look at that. We also have running times when you increase the number of parties beyond 3, which is as like a spoiler. Like there's no point in doing that. For this MPC, or to instantiate these guys, we use MP speeds, and all the code is available online in the MP speeds repository. So not surprising, we find that the fastest combination of parameters for the MPC is passive security modulo power of 2 for the 3-party 1 corruption or honest majority case. And here it's like 13 seconds for the passive evaluation, down to like 3 seconds. If we want active security, it's around 1.5 minutes if we want to do computation modulo power of 2, or around 2.5 minutes modulo prime. If we do a probabilistic truncation similar to what happens in secure ML, so this is a truncation that has a slight chance of being off by 1, essentially, and this would be for the fixed point that we have in this M, then we get an increase by like a factor of 4 for the fastest setting we have. The increase is not as fast in the other ones, but that's because this particular setting, the passive security modulo power of 2 for an honest majority, we also have other optimizations, essentially a more efficient truncation protocol in our paper. But this means like this is definitely viable as a practical thing, the one we have here as well. So I think these are quite nice results. On the other hand, if we use dishonest majority, then it's a lot slower. So these are still seconds, but now we are in the hundreds. And this is because pre-processing is very expensive when we're working this dishonest majority. So these times are of course full end-to-end. It's with both pre-processing and the online time. The online time is going to be faster, but the pre-processing is quite expensive here. Interestingly also is that pre-processing is faster modulo prime than it is modulo a power of 2. So this is why we have like the reverse situation here. Here the fastest is actually passive security modulo prime. Finally, as I mentioned, we compare against Cryptflow, which is from SMP this year. And the protocol we use is this column here, the passive security modulo power of 2 with an honest majority. And we benchmark essentially all the same protocols that they do in their paper. So it's these CFAR10 models, the ones just called A, B, C, D, which is like slightly small, plus a SqueezeNet. And in this case, we perform, depending on the network, around as well, up to twice as good, I guess. And for the larger networks, these ImageNet networks, so for a SqueezeNet, ImageNet network, for ResNet, and for DenseNet, we perform quite well, like 2.5 seconds, 18 seconds, 19 seconds versus 10, 26, 37. So I think these are all very positive results.